Welcome to this week's ICTS String seminar. It will be by Shiraz Minwalla from TIFR. He'll be talking about crossing symmetry in Chern Simons matter theories at finite NNK.
Thank you, Naveen. It's really nice to be back at ICTS after 2.5 years. Okay, so my talk today is titled Crossing Symmetry in Chern Simons Matter Theories at Finite NNK. And got it. Now maybe it'll work. Yeah. Okay, and my talk is titled Crossing Symmetry in Matter Chern Simons Theories at Finite NNK, and is based on a preprint that will hopefully appear sometime this month. Together with these collaborators, Chintan, who's my student, Karthik, who's a visiting student from ICER Pune, Umang, who was a visiting student with me from IIT Bombay and is now in the University of Chicago, and Shiroman, of course, is a professor at Dayalbagh. Okay, so this is an outline of the talk. I'm going to start with an introduction and then tell you about how crossing symmetry works standardly in theories with global symmetry, where you have to keep track of some global symmetry indices. Then I will try to explain how I believe the rules for crossing symmetry are modified in theories where these global symmetry indices interact with Chern Simons coupled gauge fields in 2+1 dimensions. The discussion here will be slightly abstract. To make it less abstract, we'll give you, I will take that abstract discussion and make it concrete in a particular example, which has the advantage of also having a test against existing calculations. And then we'll end with the discussion. Okay, so let's start. As all of you know, S matrices are among the best studied and most interesting observables in quantum field theories, also in quantum theories of gravity, though that will play no role in my talk. Okay, now S matrices are best defined and best understood in theories with a mass gap. More precisely, consider a theory which has one vacuum, just a trivial, that flows at low energies to a completely trivial state, and then has some massive particles. S matrices in these theories are very well understood. Many structural properties of these theories are properly understood, and I'm going to review two of them in this slide. The first is something we take so much for granted that you might think it's not even worth saying. It is that the S matrix takes the form identity plus I tau. Well, identity is just delta functions at forward scattering, nothing happening. And tau is a momentum conserving delta function times an analytic function of momentum. Okay, this is true. It can easily be shown in a theory with a mass gap, making one or two reasonable assumptions. Okay, the second thing that is more talked about is that this tau, this analytic function tau, has this interesting property of crossing invariance. What this tells you is the following. Suppose I have an S matrix in which something's going on. There are some initial particles and some final particles. And then I take one of the initial particles and I complex conjugate it. So I change its representation and its energy and momentum and transfer it to the final state. Okay. This is a different scattering process. It's got some different set of initial particles and different set of final particles. But the answer for the S matrix for this new scattering process is given by the answer for the old scattering process just by a simple analytic continuation of momentum. This is the conjecture of scattering of crossing symmetry. Okay, so that the analytic continuation of this tau to what you might naively think of as unphysical values of momenta actually has a physical interpretation as the S matrix of another related process. Okay, so these two properties are both true, and I would suppose are more or less proved to be true in theories with a trivial mass gap. Okay, now in contrast to theories which are massive, theories with massless particles, S matrices in theories with massless particles are less well understood, and are structurally more complicated. One way of seeing this is that sometimes these S matrices just don't exist, or are believed not to exist. For instance, in conformal field theories which of course, have massless particles, it's believed that S matrices just don't exist. Okay, because asymptotic states don't exist, because you take particles and they keep showering. Okay, so even the existence and the properties of S matrices and theories with massless particles is a more difficult subject, and one that we will not touch on in this talk. Okay, in this talk, however, the point of this talk is, however, is the observation
only in low dimensions.
In low dimensions. Of course, if you have a conformal field theory, even in 6 dimensions, you would have trouble. But for gravity, for instance, in low dimensions, there would be trouble. Yeah, so there are some, the degree of issue with massless particles varies from theory to theory. So, the best behaved theories would be like gravity in 5 and higher dimensions, where IR divergences just don't exist. Then somewhere intermediate, there would be like massive QED in 4 dimensions, where IR divergences exist, but they're so simple that maybe these Faddeev-Coolidge kind of S matrices cure them. And then there are you keep going to more complicated theories where you could go to S matrix, conformal field theories where perhaps the IR divergence is so significant that the S matrices just don't exist, and so on. So there's a whole zoo of sub possibilities within theories with massless particles. That what?
No. In your you had a sentence about equal to force triangles, and perhaps there is.
I'll tell you what I think. This is just my personal, I don't know, bias. When people, it's famously said that S matrices don't exist in conformal field theories, right? For instance, there are no poles in propagators, so how do you factorize on poles when you don't have poles? Well, sounds like a very reasonable argument. However, it's also famous that people who are good at calculating will calculate even if you tell them that what they're calculating should not exist. And that's what people have done in N equals 4 Yang-Mills, as all of you know. There's been a large and extremely successful program in computing S matrices and of gluons and N equals 4 Yang-Mills. Very, very beautiful structures emerging. Okay, the way they deal with this is that they take all the IR divergences and use dimensional regularization to regulate them away. And whatever they get, and that's very beautiful structure. Okay, so now one point of view to this is that maybe this is some intermediate step in a more complete computation when you convolute it against Parton distribution function, blah, blah, blah. It'll make sense. That would be the conservative point of view. A more radical point of view is that we haven't yet discovered the right, we've not yet discovered the right definition of an S matrix in conformal field theories. That there are good asymptotic states. They're just not particle states, they're shower states. Now, if you ask me to make that precise, I can't. Yeah. What? What is a shower state? Okay.
This energy kind of.
But it's very like that. But it's very important that it be a complete set. That you can insert unitarity in the middle. You don't want some sub-observables. Okay. So what is a shower state? What? Complete but not overcomplete. As many labels as there are in a normal S matrix, roughly. That's what I would like. So that unitarity is a clear equation. Okay. Now, this may be completely wrong, but let me tell you what I mean. Why don't S matrices exist in conformal field theories? Let's take a weakly coupled N equals 4 angles. The reason is that you've got a gluon, and then it'll split into 2 gluons. And then this one will split into 2 gluons. And since the theory is conformal, long times are same as short times, this process will never end. So there will never be a point where you will just go have one gluon. Okay, so your asymptotic states don't exist. This is why S matrices don't exist. However, maybe that's not an issue. Maybe you can go to some labeling of these jets. I don't have any good reason to say this, but somehow I feel it. But for whatever reason, that's not relevant to the talk. Okay. Good. Any other questions or comments? Something like that, but it should be something dependent on the coupling. It should know about the details of this jet. So it should be easy to compute at small lambda, more interesting at large lambda, and perhaps what they're computing is that quantity. Because it's so beautiful. If you look at the formulas, it's very beautiful.
And even at strong coupling,
there is a yeah. And then you talk about Wilson loops and so on, but I don't know, it would be nice if it existed. The question really is there something that exists and has a unitarity relation? That is really the technical question. If you call it Wilson loops, fine, but then there's no unitarity. Yeah. Okay. Okay, great.
What about the conformal bootstrap?
What about the conformal bootstrap? We will talk about the conformal bootstrap. Okay, conformal bootstrap has nothing to do with S matrices. Conformal bootstrap deals with correlation functions. There's an interesting bootstrap having to do with S matrices that will appear on the last slide of my talk. But please hang on there, show till then. Show.
Oh.
Okay. Fine. Excellent. So, but you know, despite this very interesting discussion, my talk has nothing to say about theories with massless particles. Okay. My talk is motivated by the observation that there is a class of theories that lies in between theories which have a trivial mass gap and theories that have massless particles. And these are theories which have only massive particles, but these massive particles interact with the topological field theorem. So that when you integrate out the massive particles, the low energy theory is, so to speak, a massless theory, a massive theory, but not quite. It's a topological field theory. Okay? Such a theory, okay, should not have the severe problems in defining S matrices that we see in theories of massless particles, simply because these severe problems come from continua of massless states. And there's no continuum of massless states in topological field theories. On the other hand, in such a theory, long-distance physics is governed by this topological theory. So it's different from the long-distance physics in a theory with just completely massive vacuum. So the properties, then what you mean by the S matrix, the properties of it might change. Okay? So it looks like a good place to be, a place where the thing should be well-defined and yet could be new and interesting. Okay? So, this is what my talk is going to be about. It's going to be about trying to study scattering, the structural properties of S matrices in this class of theories. Yes.
Can you think of these states as asymptotic states exist, but they are not same as usual massive theories?
Okay, it's a very good question. You will see a little bit as we go along. Asymptotic states exist, but you know, as you will see, in the theories we study, in some sense, there's no Fock space. So in some purest sense, there isn't a two-particle state without talking about interactions. That's because no matter how far you go, you can take one particle around the other and still pick up a phase. Okay? So, however, if you make a wave packet, it's fine. So asymptotic states exist in a certain sense. It's an excellent question. I don't completely understand. Okay. Okay, excellent. Okay. So my talk today is not going to be abstract. It's going to be about a particular class of theories of this sort. The particular class of theories will be, take Chern Simons theories in 2+1 dimensions and couple it to massive matter. Okay? Chern Simons theory is famously a topological field theory at low energies. So you couple this to massive matter. This is an example of the class of theories that I just described. This is the example we will focus on all through my talk. Okay. In what way?
The matter is not.
The matter is not topological, but at low energies, the low energy effective action is topological. So this is exactly. So this is the kind of theories I'm interested in. Theories that are not topological. They're real quantum field theories. They have degrees of freedom at each point in space-time. But they reduce at low energy to topological field theories. You could say we're trying to take topological field theories and put them in the service of physics. Okay. Okay. Yeah.
You say that, so basically if you integrate out, let's say, massive fermions.
Yes. Yes.
That determinant evaluates again to Chern Simons action.
Yes.
For the parity violation
Yes.
of the mass term.
Yes.
That's what you mean.
For instance.
And in expansion.
Yeah.
There are no other terms.
No, there could be other. No, for me, it's going to be very important that there is a mass. There's a separation of scales. Let's say you've got Chern Simons plus a Yang-Mills term. For instance, a Yang-Mills term could emerge as part of your expansion of your determinant. And if there is no separation of scale between that mass scale that appears in the Yang-Mills term and the massive particles you've integrated out, that's not the kind of theory. Okay, we're looking at particular kinds of theories where at low energies, it really introduces to Chern Simons interacting with massive. Okay, so the Chern Simons could be because you integrate out some massive matter at very high energies. It could be for some other reason. You could have put it in the UV Lagrange. We're not questioning how it came. Okay, excellent. Very good. Now, just a very quick reminder. Over the last 15 years or so, the reason I'm studying these theories rather than maybe some more abstract class, is that these theories have been very well studied over the last 15 years or so, for various reasons, including motivated by ADS-CFT, these ABJM theories, supersymmetric analyses, and so on. I won't review the history of this. what I will remind you of is just one fact. The fact I will remind you of is that if you take SUNK Chern Simons theories and couple them to massive matter, and you choose these matter fields to be in the fundamental representation. Okay, then it turns out that these theories are exactly solvable in the large N limit. This we showed, Spenta, me, and various other people showed in the paper in prehistory. Okay, okay. Now, since these theories are exactly solvable, you can use them to calculate interesting quantities. One of the quantities that were calculated in another paper along with Spenta and others was the S matrix in these theories. And the S matrix in these theories, we will see all this in much more detail as we go along. But is labeled by some group channels. So you can take two fundamentals and scatter them. And the fundamentals scatter in a channel where the two fundamental color indices coupled to the symmetric or the antisymmetric. You can take a fundamental and anti-fundamental and scatter it. And these scatter in a channel where the group indices coupled to either the singlet or the adjoint. Okay? Crossing symmetry would be the statement that if you knew the if you knew the symmetric and antisymmetric scattering matrices, you could find the S matrix in the singlet and adjoint channel. Explicit computations show that works perfectly for the adjoint, but works funnily for the singlet. When we look at the just from explicit computations, you look at the answer for the S matrix in the singlet channel, there are two funny things. First, this term that is proportional to identity comes this is the T matrix, the tau matrix. The tau matrix has a term proportional to these delta functions on forward scattering. Okay, so it's not completely analytic. Roughly speaking, when you write I plus identity plus I tau, the coefficient of that identity is getting renormalized. We'll see that in a minute. And second, when you look at the analytic part, the part that's not just delta functions and forward scattering, that is what you would have naively expected from crossing invariance, except that it gets renormalized by a particular factor of sine pi lambda by pi lambda. Okay, this is just experimental evidence coming from direct computations. Suggests already that structural properties of S matrices and such theories are funny. And part of the goal of our talk will be to provide a general structure to understand these S matrices, and the consistency check of the structure will be that it should reproduce this. If you choose the matter to be the adjoint representation, large N doesn't help you to do computations. You cannot compute at large N. The reason for that is that when you have adjoint representations, it's like you've got a large N theory with matrix type large N. And those theories are very hard to do computations. About as hard as to compute large N QCD, large N pure Young's theory. So it's a great question, but I don't know the answer. I mean, not from an explicit computation. By the end of this talk, I'll have a conjecture for what happens with those theories as well. Okay.
So the fact that this identity gets normalized.
Yes.
This is in 2 dimensions, it happens very often, right? Meaning only forward scattering, you just have a case, right?
Right. In two dimensions, there's nothing else other than forward scattering.
That's why it's surprising that it happens
in 3 dimensions. Right. Exactly. In these integrable theories, you can only have, as you say, forward scattering with a base. Okay. Yeah. Good.
Another question is for the non-trivial part of the scattering.
Yes.
What is known about the analytic property of that?
It's very explicitly known. I mean, there's a formula and it's analytic. It's got the same kind of analytic properties that a normal S matrix has.
For finite N?
For finite N, nothing is. I will give you a conjecture by the end of this talk, but nothing is explicitly known.
Because if it's not analytic, then when you talk about crossing symmetry,
yeah, what does it mean?
You also need to specify the path that you have to take.
Yes. That's a very interesting question, and I won't have anything.
Because in 4 dimensions, that plays an important role. Because if you prove this crossing symmetry, they have to
go around.
Go around and
right. That and here there may be some issues because the naive Feynman diagram kind of thing will put you in the same class as massless theories in 4 dimensions, whereas there's trouble in this. Yeah, so that's a
even in massive theory actually in 4 dimensions they have to go around.
But they couldn't even go around for massless theories.
Because that makes bad and
becomes bad. Yeah, so it may be that this is really a serious issue to look at, that the usual trick may require some. Yeah, so how to do the analytic continuation? In the explicit answers, it was very easy to large n answers. Yeah, but if there's some surprise at finite n, I'm not sure. Yes, yes.
It doesn't continue nicely from K0 being positive, I mean, the 0 to 2 being positive. So the statement is there are terms that look like theta of K0.
Yeah, it's the first comment about that is that, Green's functions, you normally compute for gauge invariant operators. The Green's functions you would want to compute the S matrix and not gauge invariant. So you might want to complete this using some Wilson lines. And that's going to be part of what we're going to do here. So hang on to the thing is that there is no gauge invariant local Green's function, which will compute the scattering. Hang on, if your question is not clearer by the end, hang on. Okay.
So I have a question.
Yes.
So why is the identity having a certain coefficient? I thought the identity was just
one. Right. Excellent question. This is what the slide is about. Okay. So let's first study identity. Okay, so there are two striking features of the answer that we talked about behind. First, that there was something funny going on with identity. And second, there was something funny going on with scattering. So just for completeness, I'm going to tell you how the funny thing with identity works. This we already understood in our paper with Spenta 8 years ago. This is just review. Okay, let's try to understand the following fact. Let's first try to understand why an S matrix in a massive theory goes like identity plus I times tau, where tau is analytic. Okay. One way of thinking of this goes as follows. Imagine that you're doing the scattering of two particles. So there are two plane waves coming and banging against each other. Now, there's a center of mass, so to speak, a center of mass plane wave and a relative plane wave. Forget about the center of mass part. It's not playing any role. So there's just a relative plane wave in impact parameter space coming in where the collision is happening. Now imagine you've got a theory with a mass gap. If you've got a theory with a mass gap at impact parameters that are large compared to the mass gap, the wave, nothing happens to the wave, it just carries through. Okay? So there is a part of the wave, an infinite part of it that just keeps going through. And then there's a finite part of it that scatters. That infinite part that keeps going through produces identity. And the finite part that scatters produces the tau. Okay, clear enough, right? Now this is true in every dimension. In 2 dimensions, I should move to the next slide. In 2 plus 1 dimensions, something special happens. You see, this plane wave that is coming and scattering has spatial cross sections that are d minus 2 dimensional. Okay, because it's in space and then it's some location in space moving. Now in 2 plus 1 dimensions, d minus 2 dimensional is 1 dimensional. So this plane wave in impact parameter space is a line. Now you remember what's happening. The scattering region is breaking up this plane wave into a part that doesn't scatter and a part that scatters. But now something special happens in this dimension that breaks it up into 2 topologically disconnected pieces. This segment and that segment. They can't be connected by going round because there's no round to go. Okay? Now, suppose we're doing scattering in 2 plus 1 dimensions in topologically non-trivial theory. We've got this guy going like this. And locally, nothing happens to it because the theory is massive. Similarly, this guy is going like this. Locally, nothing happens. However, it sounds plausible that, and one can check from direct computations, for instance, in the non-relativistic limit, that even though nothing's happening to this part like this, and nothing's happening to this part like this, that's locally true. Globally, these two guys pick up a relative phase. Okay? And that relative phase is basically the Arnold-Bohm effect. The Arnold-Bohm effect that if you go around some sort of trapped flux, you pick up a phase. Okay? I'm saying in this slide, I say it a little more abstractly in a way that will apply for an arbitrary topological field theory. It's a hidden object where the scattering is happening. Exactly. Exactly. Okay, so let's suppose that these guys have dimensions h1 and h2, and scattering is happening in a channel where h1 and h2 have exchanged some operator hr. Okay, then in an arbitrary topological field theory, every particle is associated with you see, the scattering process involves Wilson lines. Particle trajectories. Particle trajectories become Wilson lines in the topological field theories. Wilson lines are associated with operator insertions in the dual chiral conformal field theory. These are the dimensions of these chiral operators in the dual chiral conformal field theory. And this Arnold-Bohm phase is simply the fact that in a 3-point function, OR1, OR2, Z1, Z2 goes like 1 over Z1 minus Z2 to the power HR1 plus HR2 minus HR. This phase explains this Arnold phase. Okay. So the fact that these little wave packets get different phases here may seem locally inconsequential, but globally it has a big effect. This goes as follows. See, each of these packets gets this phase. So instead of being this plus that, we get e to the power I pi nu times this plus e to the power minus I pi nu times that. Okay, and that if the I pi nu plus e to the power I pi minus I pi nu combine to become a cosine. Okay, so in this scattering process, instead of the scattering being identity plus I tau, what you should get is cos of the effective magnetic field trapped by this Arnold-Bohm phase that we described here times identity plus I tau. And that's exactly what explicit computations, first in the non-relativistic limit by Rice and by people in the 1980s, and secondly in our large N computations, show. All I wanted to say over here was that the identity part is easy to understand and has been understood well for many years.
Sorry, just
yeah.
I mean, if I naively think of Arnold-Bohm phase, now I understood this argument, but if I think in terms of Arnold-Bohm phase,
yes,
it should have been the product of the charge with the flux.
Product of the charge with the flux, correct. Correct.
And then, so shouldn't it have been something like H1 times HR or something? If you're, this thing when you say you're scattering off it.
You're scattering one particle off another.
Yeah. Okay, so H1 with H1.
H1 with H2.
I'm just confused why.
Yeah, how does it work? It's basically this. The Arnold-Bohm phase would be T1 dot T2, as you said. But this is equal to T1 plus T2, the whole thing squared, minus T1 squared minus T2.
Oh, this is conformal dimension. So
that's right. That's right.
Okay, it's not that, yeah, not the charge.
Right. And this exactly reproduces the structure.
Yeah, that's what I'm saying.
Yeah.
It's a product.
Yeah.
Do we ever use the fact that we are in a large entity? Because it's
No. We don't use the fact, and in fact, if you do the calculation in the non-relativistic theory at finite n and k, you get the same answer. Yeah. So there are two calculations that give. First, there's a physical argument that seems to me to be very solid. Second, there are two calculations that agree with this physical argument. One at finite n and k but non-relativistic. Second at large n and k but relativistic. Okay. So I think it's just always true. Okay.
Shiraz, can I ask a question?
Of course.
So if the underlying manifold is R3 here when you do the S matrix computation.
Yes.
So if you're done just a perturbative computation, then the coefficient will just be 1. I mean, to leading order in the coupling, right?
Yes.
So if I do perturbation theory, but if the underlying manifold was say torus cross R, then would you still see a non-trivial coefficient with the forward scattering in the?
I would have to understand how to define forward, scattering on S2. Yeah, torus times R. But that's it's actually a very good question, Alok. Let me reinterpret say something about your question. You could ask, what consequence do S matrices have for the theory on T2? And this was studied by Lucier and friends, right? And they argued that in some expansion in size of torus, the S matrix can be used to produce the spectrum of multi-particle states of T2. Okay? So that is the kind of question you might want to ask on the torus. And it's a complicated question because now, in addition to, Lucia and friends had a single non-trivial vacuum, and then on top of them, that they're particle states. Here we have the states of pure Chern Simons theory as well on the torus.
Yes.
It looks like a complicated, like a long string kind of issue. But it's a question that that has been on my mind. But I don't know the answer to that question exactly.
I was thinking that if you do, it's like doing perturbation theory on a non-trivial connection, where the background connection around which you're perturbing is not trivial.
Yes.
Then you may get a non-trivial contribution. You're already in perturbation theory to the forward.
Well, Alok, even in flat space, this 1 plus cos lambda, this cos nu. In some examples, this nu is proportional to the coupling constant. Okay, so even in flat space at second order, when you go to one loop,
yes,
you should see the expansion of this cos.
Right, I see.
Okay, and in fact, there is a story. I won't take the time here to tell you that, but okay, let me just quickly tell you that the scattering of mass deformed ABJM theory, there are well-known papers that claim that one loop scattering vanishes. And one of those well-known papers has an expression for the answer. There's an answer, which is an integral, and then the paper says is equal to 0. But if you seriously evaluate that integral, you in fact find a forward scattering delta function, and you evaluate the coefficient, it agrees with what we predict from here. It's not something that the people who did that computation would have thought of looking for, because they were expecting an analytic answer. So if it's 0 in some range, it's 0. But the structure of the S matrix changes. So I'm saying that not only can you verify this, in some sense, though I think the authors did not realize it, it has been verified by explicit computation.
I have 2 questions.
Okay, yes.
So, first of all, is it an artifact of the fact that you're doing in 2 plus 1 dimensions?
Yes, it's everything I'm saying is very importantly 2 plus 1 dimension. I wouldn't use the word artifact. It is a consequence of the fact. But yes, okay.
And other thing is, I thought that your coefficient had dependence on all the 4 momenta. I don't see how they are coming out here.
Which coefficient? The coefficient of identity does not depend. Yeah. No, it does not depend on all the 4 momenta. So let's take a normal theory. Normal theory, the coefficient is 1. It's independent of momentum. Similar here. No dependence on momentum. It just depends on some coupling constants that characterize the underlying topological.
No, in your expression, you had this dependence. In your expression that you had.
Well, here, this one, yes, this I is just forward scattering delta function.
Okay.
Yes. Yeah. Okay, great. Okay. Fine. So, great. So far, we've talked about how the identity works. Okay. Now we're left with the question of what about that other factor in the non-trivial part of the S matrix? What about that sine pi lambda by pi lambda? Is there a simple structural argument that explains that as well? Now, in our paper, the paper with Sventa from 8 years ago, we'd sort of tried to propose some sort of structural argument, including some Wilson lines. And as I will try to explain, I think that argument was along the right track, but it was not precise enough, for instance, to make a prediction for what would happen at large n and k. Okay, so this talk can be taken as trying to take as an attempt to flesh out the idea that we put in that whole paper. I remember when I was giving talks at that time, I used to say I thought it was a 70% explanation of this phenomenon. Hopefully this is nearer to 100%. Okay. Okay. What? Was it 70%? I have to do the calculation. Okay. Okay. Excellent. Fine. So now we're going to take a break. We're going to veer to some technicalities. For the next 10 minutes, I'm going to remind you how crossing symmetry works in theories with a global symmetry. Theories with a trivial mass cap, massive theories, trivial mass cap, and a global symmetry. Okay? And then we will come back. This is, of course, something that's well understood, but I'm going to review it in language that will be useful for me when we discuss Chern Simons theories. Then we will come back and modify this discussion with the study of Chern Simons theories. Okay? So consider a theory that enjoys invariance under a global symmetry transformations. There's some global symmetry group, let's say SUN. Okay? And let R1 to Rm plus n be a bunch of irreducible representations of this symmetry group. Okay? Now, we are going to be considering scattering that is captured by insertions of operators that transform in the representations R1 up to Rn plus m. Okay. Now, each of these representations carries some indices, and I will often work with a tensor that lives in this product space. So it has indices in R1, indices in R2, indices in Rm, n, and so on, all the way up to Rm plus n. Okay, it transforms under group transformations the way such an index should under the R1, R2, whatever representation. Okay, now I say that such a tensor is an invariant tensor if group rotations of all simultaneous group rotations of all the indices leave it invariant. Okay, fine, just a definition. Now we want to relate this invariant tensor to scattering. So consider scattering from an initial Hilbert space. This is R1 to Rn. From there to a final Hilbert space, which is Rn plus 1 star to Rm plus n star. Suppose I'm interested in that scattering process. Okay. The scattering matrix in particular is a map from this space to that space. But any such map can be thought of as, kets in the product in the final state, bras in the initial state with some coefficients here. This is the most general form of any such map. Okay. Now, if you take this operator and transform it under group transformations, sort of obviously, these coefficients transform like tensors in this product space. The fact that this was star here maps to the fact that one of these is a ket and the other is a bra. That relative starring maps. Okay, so all I've said here is it's an obvious statement. The obvious statement is that in group space, instead of thinking of an S matrix as a map from an initial to final state, you can as well think of it as a tensor in initial state space times final state star. Okay, then transforms under group rotations like a tensor in that space should. This is just raising and lowering of indices. It's an obvious statement. Is this clear? Okay. Now, why do I want to think of it like this? The reason goes as follows. As you remember, crossing symmetry involves taking something from initial and putting it in final. When you do that and think of S matrices as maps from an initial to a final state, now you start getting confused about how can a map from one state to another be related to a map from some other state to some other state. Okay. However, the point of these of crossing is that it relates S matrices that are captured by the same insertions. These insertions live in this tensor space. Okay. So okay, I seem to have lost the point. The insertions live in this T tensor space. And so, because we've got this nice correspondence between maps and tensors, and we get the same tensor, no matter how we divide the insertions into final and initial. Crossing symmetry then is the claim that S matrices that multiply the same tensor structure are related by analytic continuation. It's now a well-defined claim because you have the same tensor no matter how you divide it into initial and final. Is this clear? Obvious statement, but it will become more interesting when we look at the matter Chern Simons series. Okay, next, one or two more technicalities, sorry for this, but again, will be needed. Next, when we study scattering and theories with global symmetries, it will be sort of useful to define a particular basis of tensors or particular basis of operators in which to expand our S matrix. Okay, so let's suppose that R1 up to Rn, you do a Clebsch-Gordon decomposition and you get a bunch of representations on the right hand side. Okay, now these representations may appear with some multiplicity. Within each group space, we choose an orthonormal basis. And we call that orthonormal basis MAI. Okay, MAR, sorry. Okay, so these are the representation indices within a given representation. A is which representation, R is which degeneracy. Okay? We choose these things to be orthonormal, because we can always do that. And then what we do is define this, what by sort of misuse of terminology, what we call a projector. We define this map, which has an M prime AR prime and an MAR. The fact that these two transform in the same representation, whether one is a ket, one is a bra, ensures that this is a group invariant object. So it's a group invariant map. And the corresponding tensor, therefore, is some group invariant tensor. Okay. Now, it's a matter of trivial algebra to check that these projectors obey these kind of identities. That is, you multiply a projector dagger with a projector, you get another kind of projector. Oh, I've forgotten some delta function here. There should have been a delta 1, 4, delta R1, R4. This thing only clicks if R1 is equal to R4. R2, R4, delta, exactly. A delta R2, R4. This only clicks if R2 is equal to R4, and then gives you the projector labeled by R3 and R1. Okay. Another thing you can check is that, what does it mean? Okay. So let's see. Let me take a particular example. I will have an example in a minute, but let me take, in general, in SUN, the case of FF going to FF. Fundamental, fundamental, going to fundamental, fundamental. Okay. This thing can couple into symmetric and antisymmetric. Okay. So now there is one M here, which is the symmetric representation, and chosen so that MM is 1. Okay. So that this will be labeled by M sim. Okay, similarly, there's an M AS. Now our projectors are M sim. So remember, in the projector, you had to have the same representation. It was, these labels only happened when there was degeneracy. In this case, there's no degeneracy, so they're just one dimension. Okay, or similarly with antisymmetry. Okay, this algebra here is the fact that symmetric and antisymmetric are orthogonal to each other. So if you take MAS, and you contract this, you get 0. But if you take M sim, because M sim, inner product is 1, it just goes back to itself. Okay, so it's that kind of trivial thing. Okay. Also, it's not hard to show, I'll have some formulas for this case later. Also, it's not hard to show that the sum of all diagonal projectors in this tilde space, the space from initial to initial, is just the identity. Okay, in this case, Ashok, this would be this M sim plus MAS is delta I1, I2, delta I2. Pil tilde. Okay, I was trying to suppress that, but let me tell you. You see, this projector here is a map from an initial to final state, final Hilbert space. But now when I multiply P dagger P, okay, this is a map from initial to initial space, because the final space indices are contracted away. Okay, so
what you mean by initial and
yeah,
the level of Hilbert spaces is the same.
No. Suppose my scattering was in H in tensor H out. Suppose this was my S matrix was going from H out star. So S matrix was H in going to H out. Okay. Now this projector here had one state that lived in this state that lived in H out, and this state that lived in H in.
So you're always defining it that way. It's not just a group theoretic thing. You always will have M prime.
Yeah, this projector is defined when you've got this bunch of representations. You take products,
right, and
then there's some division.
Yeah, so you have a division together
with the exactly, and that division is important for defining this quantity.
So you always define it with one index in the
in and the other index in the out, and then once we do this dagger operation, it's in to in.
But at the level of group theory, it's that similar objects.
In this particular example, it is. But you could have had 2 to 4 scattering, for instance. And then the final projector would be a projector relevant to 2 to 2 scattering. In to in. Right? So in the most general case, even at the level of group theory, these are different objects.
So I see. So it is on the full. So you only take the tensor product of all the instates and then decompose it. And
then exactly. Outstates and then decompose it and then exactly. And this basis very much depends on that division. I should have said that. Okay. And these, so, in the original projector to say identity makes no sense because HN is different from H out. So what does identity mean? But in HN tensor HN, identity makes sense, right? And so that's why this object in some sense is a better object. This P tilde here is a better object than P because it's a map from one space to itself. Okay, and such an equation can make sense. Okay, it's very important that it does make sense because unitarity will need this equation.
Do you care about that fact that whether it should take P dagger P or PP dagger?
If you take PP dagger, it'll match H out to H out. Makes no difference. I'm choosing one convention. Yeah.
I have a question.
Yes, go on.
So in equation 9, apart from say P tilde R3 R1A, shouldn't you also have something like P tilde R4 R2A or something like that?
No, sorry, I missed. There was a typo in this equation. There should have been a delta R2 R4.
No,
this thing
apart from the delta function, I mean,
yes.
Should there be multiple terms? Why should there be just as R3 R1 in the final state?
You see, because this thing here, can you see, Shomdeep?
Yeah.
Can you see my pointer? This thing here, when you contract with another thing there, is diagonal. It only clicks when A's are equal and when R's are equal. So that gives a delta. And then what is left behind is what you get. Delta A prime. So I've missed all the delta. Sorry. Delta A prime, delta R2. Is this clear, Shomdeep?
Yeah.
Okay, excellent. Very good. So now, why was it important that these projectors summed to give identity? I'm assuming that time is not a serious issue in ICTS. Okay. Okay.
Hi, Shiraz, could you just once more clarify the difference between P tilde and P?
What? Sorry, say that again.
Could you just once more clarify the difference between P tilde and P?
Okay. P here is this object here, where this guy lives in the initial Hilbert space, and this guy lives in the final Hilbert space. P tilde is a similar object, but where both this and that live in the initial Hilbert space. Notice that if you take the dagger of P and contract it with P, you will get a P tilde. Because this will survive, and from the dagger, the other guy will survive. Both will be in the initial.
The initial final distinction is not clear to me because these are just irreducible representations, right?
Excellent. So I should have said this more clearly. Let me say it more clearly. While so far my tensors were only defined on some product of representations, in order to define this projector, there's a new element I need. I need a division of these representations into what I'm going to call initial and final. Some arbitrary division. You take these representations and divide them arbitrarily. Okay? One set I call initial, the other set I call final. This object here depends on that division. One set could be empty, but then it will not be interesting because for scattering it will play no role. But at the level of group theory, it could be. What? Yeah, no, but that would be scattering of lots of things to nothing, which will never conserve energy. Right. So it will not be useful for scattering.
So is label A?
Yes. A is a representation.
A is the degeneracy.
No, R is the degeneracy.
Oh, sorry. R is the
degeneracy and A is the representation.
So you pick out the same representation in the initial tensor product
and the same in the final. Otherwise, it's not group invariant. Okay, we want only group invariant structures. So this is needed. That A here, same as A here, is needed to get group invariant operators or group invariant tensors. But there's no constraint on R. That's allowed to be whatever it is.
So some of these A's are being called initial and some are being called final?
Oh, let me say it again more clearly. I take all the initial representations and couple it to whatever I get. I do the same for the final representations. All the final representations and couple it to whatever I get. A just labels what representation appears in this tensor product. It appears with some degeneracy in initial space, some other degeneracy in final space. But A is just labeling a group representation. Okay, this, as Rajesh said, this P would be empty if a particular representation did not appear both in the tensor product of the initials and the tensor product of the finals.
I see. Okay. Yeah, I get it.
Yes. And then there is no group invariant tensor corresponding to that representation.
That's a selection.
That's a selection rule. It's just group invariance, as you said. Excellent. Good. Okay. Now, so we've got this structure, which is, very simple algebra to see. And we've got this equation, which is also easy to prove. Now, what we're going to do is to work with these projectors or the tensors corresponding to these projectors and take the S matrix and and write it as a sum of functions of momentum. These are the non-trivial things that we want to compute. S R R prime A times these index structure projectors. Okay, since the S matrix has to be group invariant, it has to multiply in particular group invariant index structure. This is the most general form of the S matrix. Easy to show that this P A R R prime forms a basis for the space of all group invariant tensors. Okay, so this is the most general S matrix. Now, the important thing is unitarity. How does unitarity work for these equations? Unitarity works as the equation S dagger S is equal to 1. You just plug this in to the unitarity equation and use this equation. Also use this equation. Then what we will get is on the right hand side and the left hand side tensors from initial to initial. You've got a basis of tensors, equate coefficients of independent of the basis elements. When you do that, you get this equation. Okay. What this tells you, although I've not written it in a way that makes it completely manifest, this is just matrix multiplication in this degeneracy space. Because this R prime index is contracted. When you make this a dagger, this will become S dagger is equal to SI. So what this tells you is that the unitarity, when you work with this basis, the unitarity equation becomes very similar to the unitarity equation that you would have got had you not had these group indices. The only difference is that in each representation space, you've got a matrix multiplication as well as the usual momentum space convolution. The matrix multiplication is associated with the degeneracies. Degeneracies in that space. In particular, if all degeneracies are 1, this is the usual unitarity equation, as will be the case in our example. Yes? SI is the same forward scattering delta function that we encountered at the beginning. Sorry, I call that SID in the beginning. Yes.
So that doesn't have any group labels.
This is just a function of momentum.
So the A label is just.
This works A by A.
A by A. So it's for each A and the right hand side.
That side is independent of A. Yes.
And is SI really the item?
No phase, nothing, no phase, no factor, just identity, probability conservation. What? Because of 10, exactly. 10 was crucial for this. Okay, excellent. Now, so we've understood how you can take these S matrices and decompose them in this projector basis. We understood how unitarity works in this projector. But as several of you have commented, this projector basis depends on the division of the representations into initial and final. Now, crossing precisely changes that division. Okay? Yes. 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 I'm sorry. Yeah, you're right. This should have. Yeah, I've got here sum over final states. Yeah, for the contribution of any one process is some finite matrix, but then the sum over all processes. As you say, there's 2 to 2 scattering that contributes some amount, 2 to 4 scattering that contributes some amount. You have to add them all up and then you get the right.
We've already given R1, R2. Right?
Yes.
There will be a finite number of R prime and then there will be the usual momentum integration.
And the usual sum over final.
R prime will be finite. There will be a finite sum over finite number of R.
For any given final state, it's finite. And then there's a sum of the final states.
So the Fi is just for the two, let's say it's just for the
initial state. You see, Si is identity on initial goes to initial. So that is universal, independent of what you're scattering in the middle. You see, all the intermediate final state indices get contracted. That's why you get such a beautiful universal answer. Clear?
So this is an equation where you take say you are trying to state that unitarity on initial channels.
But and that not only does hold, I mean, not only are we saying it does hold, it's a matter of algebra.
But that's what we say.
Exactly. Exactly. We're decomposing the unitarity equation, as you said, intermediate color channel by color channel. Exactly right. And the nice advantage of doing this, using this nice basis, is that the equation in each channel looks familiar. Okay, apart from degeneracies, it's the usual equation that you would have had without having color indices.
I mean, there is also a non-trivial, maybe trivial part, which is that the matrix element of the right hand side.
Yes.
Initial result part should be zero.
Yes, that's this right hand side. Yes. This SI has that.
Yeah.
SI is this delta product of delta functions.
Yeah. That also includes the fact that the number of initial should be the same.
Yes, but that's the structure of this equation because the final things have been contracted. As you say, identity makes no sense unless you're going from one Hilbert space back to the same.
Yeah, but I'm saying that you also have to check that if you calculate the matrix element of identity between 2 and 4, that's 0, right?
Right, but that's by definition. Identity.
But the right hand side, the left hand side,
it should be 0. I agree. That's right. Right. You're saying that that should be somehow put into this. Yes, I agree. That this is within 2 to 2. And in addition, you should also say that 2 to 4 is 0. I agree. That's not put in this equation. I agree. Okay, excellent. Okay. So now, as we've said, this way of proceeding depends on the division of particles into initial and final. And crossing changes that division. So the natural basis for studying unitarity in one channel is different from the natural basis for studying unitarity in the crossing related channel.
it changes the division of the number elements.
You could also change number of insertions. Yes. Now the total number of insertions. Yes.
Total number of terms in this sum should remain the same.
Total number of terms will remain the same. It's because the total number of terms is just a basis for finding all group invariants of the product. Exactly. So total number of terms.
The product of the initial space.
No, I think Ashok is saying finally the total number of projectors. Yes. So individual numbers will change, but the total number of projectors will not change.
Yeah, but in your equation, this A will depend on the division, right?
This A will depend on the division. You might get different A's.
Right.
But I think Ashok's limited point was that just count the total number of projectors. No matter how you do the division, you get the same. Because these are just different bases for the same space. The group invariants of the products of R1 to Rm plus N. Okay, excellent. Now, so because this division changes, the basis changes. But you see, because we've worked in this tensor language now, both of these are tensors in the same space of tensor products of these representations. And so we can write one nice basis element in terms of the others. Okay, and that's how crossing works. Crossing then relates these coefficients of these coefficients here by take these p's, write them as linear combinations of the p primes. The p is relevant for the crossing channel. Okay, and then whatever you get after analytic continuation should be identified with the S matrix in front of that cross, that channel. Is this clear? Okay, great. So this procedure that I've outlined in words allows you to deduce the connection between the S matrices and the two different channels. Oh, is that very
Sorry, just,
yes.
Like you said, for the fundamental.
Yeah, in fact, that's the example. Yeah.
So there, maybe because the A will be for the first one, the A was symmetric. And
symmetric, antisymmetric. Second one is singlet and adjoint.
Singlet and adjoint.
Adjoint.
So
Again, two. Completely different, just the number is the same.
The number is.
Nothing else.
Yeah. And but then what were you saying that what is it that you're going to relate?
Yeah. So now you take the, let's say that you have P singlet.
Yeah.
This is some invariant tensor in the product of these first. Write that as A times P symmetric plus B times P antisymmetric. Because both P symmetric and P adjoint, one set, and P symmetric and P antisymmetric, that's one set, and P singlet and P adjoint, that's the second set, are bases in the space of invariant tensors on this product space. Any one can be written in terms of a linear combination of the others. So do that and plug that in, and then collect the coefficients of P symmetric.
There are two different channels here.
Yes.
Considering and trying to relate the basis.
We're relating the group.
It will transfer everything on one side and.
Yeah, exactly. That's this tensor product thing. Right? Because
you could transfer everything on one side, then express everything in that basis, and then.
Yeah, that's these invariant tensors.
Yeah.
All of these operators map to invariant tensors, and they're the same invariant tensors, same space of invariant tensors. So in that space, you can do this manipulation. Clear? Yeah. Okay, excellent. So
I have a question.
Yes.
So when you have 2 to 4 scattering, wouldn't there be more than 2 ways of decomposing the intermediate states?
There might be. It depends on details. But however many ways there are, or this formalism holds. Only in the example have we ever used that there are only 2 ways. The formalism was completely different.
No, in 2 to 2 scattering, I understand that you have either symmetric and antisymmetric and singlet and
no, but even that is 2 to 2 scattering when we look at fundamental, anti-fundamental. Take 2 to 2 scattering with complicated representation. Even there you will have many channels. For instance, in SU2, you take J1, J2, J1, J2. You'll go from some representations will go between J1 minus J2 and J1 plus J2. Right? And if J1 and J2 are large, that's lots of representations.
Yeah, so my question is then what happens to the crossing symmetry?
Crossing, it's the same principle. Any one division allows you to write down this basis elements. The other division allows you to write down the other basis elements. You find one set of the basis elements of one as linear combinations of the basis elements of the other. Nothing here is used 2-dimensional. Is this clear?
Yes, yes.
Okay. Okay, what's sort of important is that now we are able to formulate both crossing and unitarity in the same language. As you will see that. Okay, now let's quickly, I'm sorry I'm going so slow. Yeah, go on.
So this, for example, state space is state.
Yes, it's group theory. In fact, it's what people call 6J symbols. Okay, so yeah, right. It's simple group theory. What we're going to find in the Chern Simons theory is more complicated group. What it might turn out is that this is 6J symbols of the quantum group, whatever that is. Yeah. Okay. Okay. Yeah. Yeah. People, my undergraduate student who's visiting me, Karthik, who's very good at this kind of thing, has located chapter 16 in one book in which they define 6J symbols of the quantum group and has been trying to compute it for these. You know, the book seems totally useless because it's a chapter, but you can't do a single computation. I can't do a single computation. But if we can compute it and find what we get, we'll believe it. Okay. Rama may know. Yeah. Okay. Okay. Fine. Now, yeah, this is our example. I'll try to go faster. I'm sorry. Okay. Let's look at FF goes to FF. So this is the space where you have 2 insertions of F and 2 insertions of the antifundamental. Okay. Let I and I prime represent fundamental indices. J and J prime represent antifundamental indices. Down is fundamental, up is antifundamental, so on. In the space of tensors, in invariant tensors made out of these 4 indices, there's an obvious 2-dimensional basis. This product of delta functions and this product of delta functions. This is not a projector onto anything, but it's some obvious basis for the space of invariant tensors. Okay. And now, I haven't even told you this, but you know, when we made this map between operators and tensors, Using how we know, the fact that we know how to take Hermitian conjugates of operators, we inherit a rule for Hermitian conjugation of these tensors. And the rule is simply that you complex conjugate all coefficients and raise and lower indices. Change representation indices to R star representation. Okay. So for instance, the tensor corresponding to T dagger is just, flipping I and J up and down. Okay, similarly to E. This is what comes out when you look at the map between operators and these tensors. Because we know how to take Hermitian conjugates of the operators, and we know the map. So that you get some inherited rule, this is the rule. Okay. Something else that I didn't tell you about is that when we have two operators, you know how to multiply them, because that's what operators are good at. They're good at multiplying each other. But what rule does that give you if you've got two tensors? How do you multiply two tensors? Turns out that the rule, it's very intuitive. You can only multiply two operators when the final state of one is the initial state of the other. So you can only multiply two tensors when they've got a set of common indices, but some are upper indices and some are lower indices, corresponding to final representations. And the rule for multiplication is simply that you contract those indices. You glue those indices. Easy to check using this map to operators. Okay, fine.
Usually think of this global symmetry as the Chern Simons.
Yes, it will be gauged eventually in Chern Simons. Yes.
Yeah, otherwise you could give these rules without talking about symmetry at all, right?
Yes.
As long as you consider a conjugate to a given particle,
yes,
you can keep the rules
once and for all. Yes, but it's important for me to be in this language because for the Chern Simons. This is just complicated way of saying well-known things, but a way that will be useful.
But when you consider S finite n, you are not going to consider finite n.
We will.
So
N and K will be finite.
So, but then the cases will have these finite n
Truncations.
truncations.
You will see how that comes. Yes. Okay. Excellent. So far, now we want to move to this projector basis. Easy to check that the projector basis for the singlet and the symmetric and antisymmetric is simply given by the symmetric and antisymmetric linear combinations of these, obviously projecting onto symmetric and antisymmetric. And then you need the by twos to keep track of normalizations. So, and the relevant multiplication rules that I gave you in abstract detail can be very explicitly checked here. We expected that TS dagger TS was equal to basically TS, and that works out. TA dagger TA is TA, and that works out. TS dagger TA is TA dagger TS is equal to 0, and that works out. Okay. Similarly, the projectors for fundamental anti-fundamental scattering are these guys. This product of these delta functions divided by n, so just one of these. This guy divided by n. And the projector on the adjoint is the other guy minus this guy. All this easy to check. Okay. Once again, you can check the multiplication rules go as follows. Give you what you expect. That Ti dagger Ti goes back to Ti. Ta dagger Ta goes back to Ta. And Ti dagger Ta is Ta dagger Ti is equal to 0. When I say goes back to Ti and goes back to Ta, in this particular example, it makes sense because in this particular case, initial and final spaces are the same. In general, it goes to another kind of projector. Okay, fine. Now, therefore, using this, since we've got an explicit construction of both Ti and Ta in terms of these, neutral basis elements, and also an explicit construction of Ts and Ta in terms of these neutral basis elements. Okay. Yeah. The small button. Okay, fine. For this reason, it is easy to find Ts in terms of Ti and Ta and Ta in terms of Ts and Ta. You do that, you do it with some algebra, and this is what you get.
N is SUN.
N is of SUN. Yes, the rank of SUN. Okay. And therefore, by doing, putting this into the decomposition of the S matrices and then equating coefficients, you find the relationship between the identity channel scattering matrix and the symmetric and anti-symmetric scattering matrices. Similarly, adjoint channel scattering matrix and symmetric and anti-symmetric scattering matrices. Okay, is this clear? So these are the rules for crossing invariance in this theory. Okay, with these, keeping track of these global symmetry indices. Nothing great has happened here. Any reasonable person who wanted to derive this would have been able to do it. I've just put it in language that will be useful in what follows. Is this clear? Excellent. Okay, now we get to the real topic of this talk. The real topic of this talk is how does this structure extend to scattering in matter-Chern Simons theories? Okay, so give me a serious deadline, please. For one will definitely start, but that's okay. Thank you. I could, but then I would have to rush. Okay. See what you'd like me to finish in 15 minutes? Okay. Huh? That's okay. Okay, fine. Okay, fine. Excellent. Okay, so now we're moving on to the Chern Simons. Now I'm going to give you, two slides of how we think of it before we get to formulas. Okay, the way I'm going to think is as follows. If I want an S matrix, I can extract the S matrix as a transition amplitude between an initial state and a final state. Okay, the initial state and final state can be extracted from path integral where you specify initial conditions at initial point, final conditions at the final point. Okay, now this path integral we're going to perform on a cylinder. And despite the way we've drawn this cylinder, we're going to think of the cylinder as being more broad than tall. Okay, cylinder is very, very big compared to the mass, both in breadth and in height, but the breadth is more than the height. Because we don't want particles to be able to go and hit the sides of the cylinder. Okay, that will be will give us more complications. So a particle should, but never go and hit this side. Or think of that as almost going up to infinity. No, but I'd like to be able to have non-trivial representations of the initial particles. If you put things on a sphere, you're forced to be in the segment. So I don't want to do that. Yeah. Perhaps you can. Since most of what I'm going to be saying will be for the topological theory, it may not even make a difference. So perhaps you can. I just find this way clearer to think. It's now very popular to work with Penrose diagrams, but I'm doing massive scattering, right? It doesn't seem a very natural thing to do. So then this is future infinity. I mean, why should I depict it as a dot on a Penrose diagram? It's the space, right? Okay. 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 Okay.
So now, just one clarification.
Yes.
You said that you are taking the breadth is more than the height, but if I fix my initial and the final state, then would it still possible that it is going to hit to the side?
Yeah. So what it means is that we want to fix our states in the interior of this disk, not have the state go too far near the edge. That's really what I mean. All the data I'm going to specify well away from the boundary. Okay. Now, there's something else you can do. And that's also interesting, but I don't want to get into that. You see, because if you have a particle going and hitting the boundary of space, then it changes the scattering process. It must reflect off that boundary and so on. We don't want that to happen. We want it to be scattering in flat space. So the boundary should just be an IR regulator, should not be playing a part in dynamics. Is this clear, Sachin?
Yes, thank you.
Okay, fine. So now what we're going to do is to try to write down an expression for the final to initial sort of S matrix. I'm going to be very schematic in these equations. As I said, this S matrix can be extracted from this initial to final transition amplitude, which was a path integral with some initial conditions and some final conditions. Now, this path integral can be performed by doing this group here, this path integral over fields. Okay. But now we can take the path integral over the matter and work in the world line representation to represent the path integral over matter into a sum over various world lines. Okay. Then we interchange the order of sum and limit, take the particle, do the sum after doing the integral over the gauge field path integral. And so each of these world lines now turns into a Wilson line in the pure Chern Simons theory in which we're working. Okay, so our full path integral is a sum over trajectories of Wilson lines. Each of these trajectories is weighted by some action, length of path or whatever. And then it's also the expectation value of that Wilson line in pure Chern Simons theory. But the expectation value of Wilson lines is topologically embedded, so we can pull it out. Okay, and therefore we can break up the sum of paths into sum over topologically distinct chambers of paths times the volume of all the paths within that chamber.
Chamber, you mean just topologically distinct?
Topologically distinct configurations. So far. Yes, and you will see. If that happens, then we will need to include interaction factors. How that works in the Chern Simons theory, you'll see. Yes.
You go over the argument again, please.
The argument is simply this. We want to evaluate a path integral from initial to final boundary conditions. Now that path integral, as far as the matter is concerned, we evaluated in particles, summing over particle trajectories using the world line representation. Now for any given particle trajectory, the gauge theory path integral can be done and gives you the expectation values of some Wilson lines with some particular initial and final insertions. We'll come to that. Okay, but it doesn't care about the precise path, only the topology. So all things that are topologically equal, we group together into this trajectories in a given chamber. And so we write the final answer as sum over topologies, some function times this Wilson line.
Okay, so this particle trajectory, I mean, when you consider the world line, it usually has a kinetic term, right? X square, x dot.
All of that goes into here. This is this S matter. We're including the weighting factors from length of the line. All that's included. Okay. That's what's going to give you these non-trivial S matrices. So far, we've not done anything, but you will see where that comes. 1 minute. Okay, let me tell you immediately. The fact that we're not allowing for reflections there plays the following role. In Chern Simons theory, apart from whatever matter degrees of freedom you have, you also have a Hilbert space that lives on the bulk. But the Hamiltonian for that Hilbert space is 0 unless you have Wilson lines coming and hitting it. Since we have no Wilson lines going and hitting it here, that Hamiltonian there is 0. And so we'll be able to shrink this region and make this path integral that for a sphere once we go to Euclidean space. That's really where that's one place to use it. Yes.
You have a theory which is topology. So there's no measure.
It's yes.
There's no background measure.
Yes.
And then get to make a difference between space and time. It's really majorial difference.
Yeah, but look, it's only topological as far as the low energy theory goes. The matter is not topological. So in the full S matrix space and time are sort of different. But as you guessed, once we word the problem purely in terms of Chern Simons, we will allow ourselves freely to continue to Euclidean space. Okay. Okay. Now, we've reduced the problem somewhat because we've got it over a sum of topologies. However, the number of possible scattering topologies is still infinite. However, we now use Witten's famous observation that all Wilson line configurations with given endpoints are labeled conformal blocks, and the space of conformal blocks is finite. Okay, which means that every one of these WTs can be written in terms of linear combinations of a finite basis. Okay, plugging this in here, we can rewrite our S matrix as a sum of S matrices multiplying a basis of conformal blocks, a finite basis of conformal blocks, rather than this infinite basis of topologies. Okay. Now, since yeah.
So this sum is still in the definition of SI.
Yes, in this definition, there's.
No, in the definition of SI.
In the definition of SI, there's an infinite sum. But this is the formula we will finally. Yes. Okay. Now you see, if you compare this equation to the one we had before, 5 transparencies ago, where we had SI, sum of S is equal to sum over SI TI, you see that these GIs are playing the same role here as the invariant index structures were playing in the global symmetry theory. So we've got the first element of our map. The invariant global index structures are replaced here by conformal blocks.
And they are labeled by only those.
Those finite representations.
But so when you write this ST, that's just a normal Chern Simons Wilson loop expectation value summed over with
Yes.
your given.
Yes. Yes. Even at this stage, just normal with Chern Simons Wilson.
Yeah. So and this is just breaking that up into.
Now.
So, no, you had ST. You wrote STI. Oh, sorry. This ST is sum over topologies.
T is topology. ST is all the paths within a given topology.
Yes.
Okay. Now we include all paths within a given topology and then sum over topologies as well, but labeled by this I, where I is now a conformal block. Yes. Yes. Yes, you will see. You see. Basically, because conformal blocks only care about the endpoints, doesn't care about what's happening. You will see. Okay.
This Wilson line expectation value is just a Wilson line dress. It's just a dressed Wilson line, right?
It's a expectation value of Wilson line in pure Chern Simons.
Yeah, but it just means that it's dressed by all possible corrections, all possible loop corrections, right?
All possible loop corrections in pure Chern Simons theories. And we know the values of Wilson lines in pure Chern Simons theories exactly. So just that answer, that exact answer.
It's an exact thing.
Exact thing. Wilson lines in pure Chern Simons theory are known exactly. That's what got Witten the whatever prize, some prize. This feels like. Okay, What?
Why does it decompose into conformal blocks?
Okay.
Sorry, Somdata, if we could table the discussion to the end. And also a general request to the audience, because we are running short on time, if we can reserve questions to the end, that would be very...
I mean, urgent questions. If you're not following, please say. Yeah.
But any comments or any long-winded discussions we could have towards the end of the talk.
Yeah.
Thank you.
Yeah. So a conformal block, Shomdeep, this is a long story. I recommend you read this paper called about Jones polynomials by Witten. It's a beautiful paper. It explains this, but I don't have the time to explain it. Okay, fine. So, as I said, if you compare this formula with what we had earlier, you see that these conformal blocks are playing the role of index structures. Okay. One more thing that supports this is the following. If you compute conformal blocks and take the limit k goes to infinity, it's easy to check just as expressions in hypergeometric functions. We did this check for 2 fundamentals and 2 antifundamentals. The conformal blocks, the position dependence trivializes and just reduces to index structures. Okay, so conformal blocks are very naturally the finite k generalization of invariant index structures. Okay, now in order to understand how to deal with scattering, we needed to be able to multiply 2 index structures. We did that by contracting indices, common indices, if you remember. How can we multiply 2 conformal blocks? Well, the answer is that we should contract common indices, but in the sense of Wilson lines. Let's see what that means. Suppose I have a conformal block here. As you see, Loga, this has interactions. I'll explain to you in more detail how that works. Okay, and I take this conformal block and I sort of flatten the part where the final states are. And I have another conformal block with the same final states. And once again, I flatten that part. Then the rule from going from a block to its bra is to reflect around this flat part and to change the direction of flow of all color indices, change representations to anti-representations. Okay, so if I want to multiply one conformal block like this with another conformal block of the same sort, I take that second guy, I reflect it, I get this guy, and then I just glue this diagram in the final states to get this guy. This is the rule that tells you how to multiply 2 conformal blocks.
It's easier to see in your cylinder.
Go on. What do you mean?
So you have these initial states at the bottom and then states at the top.
Yes.
You have one more cylinder.
Yes. Turn it around and put it.
And then you do your...
Yes. 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 Though the one thing that I've done here that was implicit in the cylinder, though I said it in response to this question, is I've contracted away infinity to make it a sphere. So to make it a well-defined path diagram. Okay, this, by the way, the same procedure was used by Witten to define the inner product in the space of conformal blocks, except he glued not some of the representations, but all of them. What we're doing is square root of Witten. Okay, our definition of multiplying conformal blocks is a square root of what Witten did for defining inner products. If you also take the remaining indices here and glue them, you get Witten's inner product between these two blocks. Okay. But clearly, physically, this is the right thing to do, right? Because the particles are just continued. Physically, it's clear that this is what we have to do. Okay. Now, there's one warning I want to give you, and that the Wilson line representation of a block is really a representation of the block plus a choice of sheet structure. To see that, notice that if you take this Wilson line representation of some block and take, what have I done? R1 around. Yeah, take R1 around R2 like this. You get another Wilson line, which is different. In block language, you're going to another sheet of the block. So when I tell you, I've told you how to multiply two blocks, what I've really told you how to do is to multiply two blocks with given specified sheet structure. Because I've told you how to multiply them once I've given you the Wilson line representation of the block, and that comes with the specification of sheet. Okay. Now, now what we want to do is to define projector blocks. This exactly, but that's already done. That's already done in this formula.
Yeah, but you don't have to calculate SI, you are not using this.
Yeah, as you will see, Ashok, there are very few computations in this. It's all structured. We somehow managed to put it in this form, then I have to deal with this SI. Feynman diagrams do this sum. They do everything, right?
But if you want to do it this way,
then you would have to explicitly sum. Right. Right. Okay. Fine. So I've shown you how to multiply two blocks. Okay. This will be needed for unitarity. Now, the next thing I need to show you how to do is to find these projector representations of blocks. Let me show you in a diagram. You see, Loga. In fact, there was not that well-known paper of Witten written 6 months after his original Jones polynomial paper, in which he discussed many beautiful things, including these things I'm telling you about. There is, in fact, a simple orthogonal basis of conformal blocks that you can write by using Wilson lines which have interactions in the bulk. Okay, Witten studied them in detail, and that study was invaluable for our paper, for what we're doing now. Okay, so in particular, Witten gives you this construction of orthogonal conformal blocks. Okay, take R1, R2, R up to Rn minus 1, and you want to fuse it to Ra. You just fuse like this using the Wilson lines. This is clearly the Wilson line analog of the group theory fusing we did. Okay. Similarly, once you've got this is like one of these MAs. This conformal block is like one of these MAs that we had. You have to do the same for the final particles. Then you have to glue along this MA. That's this. You fuse these representations made in Ra. You fuse these representations made in Ra. And then you glue. Okay. This is a representation of a basis of all conformal blocks. And Witten has shown that it's an orthogonal and complete basis for conformal blocks. Okay, there's some subtleties I'm hiding here. What are the 3-point functions? How do these truncations that Rajesh was talking about come about? All this is completely well understood. Okay, you can read it in our paper, or if you want a lengthier exposition than Witten, or you can read it in Witten's paper. Okay, is this clear? So once again, you can define these conformal block, these projector types conformal blocks. I've suppressed some details of normalizations and so on, because it gets a bit technical. You'll find it in our paper in great detail. Okay, once you get all your conventions correct, now I told you both how to make conformal blocks, projectors, as well as how to multiply them. Taking adjoint of a block is by reflection. So I've also told you how to take adjoint. Okay, so now you can compute this projector block dagger with projector block multiplied and see what you get. You get exactly the same algebra as with the projectors that we had with classical group theory. Okay, and something else you can also show is that you get the same decomposition of identity that you had in classical group theory, where identity is the block where Wilson lines just go straight up. You've got a bunch of insertions, bunch of in the past, same insertions in the future. Wilson lines just going straight up is identity. Why is this identity? It's identity because it's easy to show that if this is your definition of identity, then identity multiplied by any block is the block itself, because it's not changing anything.
So the blocks are almost like the group basis thing, but except I guess that unlike a group, they're not associative, but that doesn't play any role in your,
what do you mean they're not associative?
I thought these are, I mean, it doesn't obey, it obeys. Group multiplication is not like G1, G2, G3, but I guess you never encounter G1, G2, G3.
Well, you know, we only ever multiply blocks in this fashion. But in this fashion, they're obeying exactly the same algebra as those classical things.
Right, for this, because that's the distinction between a quantum group and an ordinary group.
Yeah, but these are not group elements. These are these projectors we built out of the structure. My feeling is that these guys have exactly the same algebra as the classical guys. We've even given a paragraph in our paper for explaining.
Truncation has to be.
Of course. So this is the same algebra on a truncated space.
It's only, but no, and what is the difference between, I mean, group theoretically, what is the difference for the same representations?
Yeah, so in this, you will get these RAs different number of multiplicity times. So these R primes will run over different values, right? Because you'll have the truncations you're talking about. Okay, but apart from that, the structure is basically identical. These indices. So when I say identical, of course, the details are different. The Klebsch-Gordons are different. Okay, the Klebsch-Gordons are different. That's the reason why you get these truncations. Okay, but once you put it in this form, as far as I can tell, the algebra is just the same. So now I multiply one more on the left hand. Even the 3 thing will just be the same, it seems to me. Even doing 3 is a bit odd because this is G tilde and these are G's. To the extent that you can define it, it looks just identical in structure, apart from the fact that the indices are running over different values.
Yeah, but it's not like you're truncating the original group
No,
theory.
no, we're not doing that. It's a new group theory.
Yeah,
but that's
no group.
It's the new whatever. It's these.
I mean, the multiplication of G and G dagger is by prescription in this path integral on this.
Sure.
So when we do that, the truncation is.
I understand that, but I'm just worried about the group theory and just at the level of as a group. I don't think you have the group structure anymore. Once you go to the
but these are not group elements, you know.
They're not group elements, but you're. But I'm trying to. Anyway, we can talk about.
Fine. Fine. Okay, but yeah.
You define the identity to be these Wilson lines which don't go around each other.
Yes.
And also they should framing.
Yes, the framing also requires that you have the same framing value on both sides because now it's initial to initial. So that statement makes sense. And that there's no topological whitening.
Between different Wilson lines, you want that kind of.
From here to here, it's trivial frame. You're going from same initial to initial. The endpoints are specified. Yes, but your prescription is that you don't. Yeah. And that's well defined because these endpoints are. And that's identity. Yes, exactly. I should have said every time I draw a diagram here, I'm working in the vertical framing convention. Okay. I'm not getting into such technicalities, but it's very important to get the answers right. The phases are hell to keep track of. Yeah. But we've done it very carefully. Okay. Fine. Now, because of this, because all these algebraic properties are the same, unitarity works in the same way when expressed in terms of coefficients of this basis, as it did in the classical case. Okay? So now, once again, the problem of crossing is simply this. You've got these basis blocks associated with one split, basis blocks associated with another split. Rewrite the basis blocks in one split in terms of linear combinations of the basis blocks in the other split. And that gives you crossing. But it's important to do it in this basis because this is the basis in which unitarity takes the canonicals. Is this clear? Okay. Now, very quickly, I will try now to end in 10 minutes. Yes. Which? Yeah. AB will be like these, like the 6J symbols. You write one conformal block in terms of another conformal block, where as long as the endpoints, you see this conformal block plus choice of sheet structure. So not quite monodromy. It's like writing singlet and adjoint in terms of symmetric antisymmetric. It's like a 6J kind of thing. Yeah, it's a different, yeah, exactly, different OP channels. Cyborg more have a name for this, but I can't remember. F or something. Fusion, F. Yeah.
Could you go back to the previous slide? The previous slide. Yeah, this one. So here, when you're talking about crossing symmetry, what exactly, I mean, how are you decomposing the S and the T channels? Because you have multiple conformal blocks. And
so in general, crossing relates what happens with one division of representations into initial and final and the second division. So one division and the second division, each of which have their own structure like this. And so you decompose these blocks in one division in terms of these blocks in the other division. That's what is relevant for crossing. Okay, so now let's quickly look at one example. I'm sorry to have gone on so long, but let me try to hurry this. Let's look at the one example. Let's suppose we look at fundamental, antifundamental scattering. Okay, so you have these blocks up to normalization are given by this in the symmetric channel where you exchange symmetric with an explicit Klebsch-Gordon vertex here. All this much beautifully studied by me. Okay, and a second block where you exchange the antisymmetric. Okay, now we want to actually make the projectors. How do we do that? Well, first thing I want to do is to check that these two things are orthogonal under compounding, under multiplication. Okay. Now that's very, oh, it's here. That's very easy to see. Take this diagram and fuse it. So you get the multiplication. Okay. And then this diagram is in this form where this is this. Now cut this path integral here. This little cut path integral is a 2-point block, but one insertion is the antisymmetric, the other is in the symmetric. Any 2-point block with two insertions in which the insertions are not conjugate to each other vanishes. Therefore, this thing vanishes. So this is 0. Okay, is it clear? Okay, how do we compute the normalization to make them actually projections? Okay, do the same thing. So we get this and this. And now what we do is do the same cut. Once again, we've got a 2-point function. But this time the 2-point function is not 0 because it's either sim and sim or antisymmetric and antisymmetric. However, every space of 2-point function blocks has one dimension. Therefore, this is some multiple of this. Because this is another representation of the same 2-point function block. In order to find this alpha, all we have to do is to take inner products on both sides with this block. We take that inner product and we get a formula for this alpha. It's this Wilson line divided by this Wilson. Okay. This is Witten's inner product. Okay. This inner product produces that funny thing by doing this with this. Okay. And therefore, finally, we've got a formula for the normalized projector blocks, which is this. This, by the way, is the quantum dimension of the corresponding representation. It will play a role in what comes about. These things will cancel in all final answers. Okay, so these are a normalized projector blocks in symmetric antisymmetric. We do the same thing for singlet adjoint. Once again, you can check that the multiplication of these two blocks is 0 if one is singlet, one is adjoint. Same argument. Okay. Once again, you can check that, of course, it's not 0 when with singlet adjoint. Once again, you can compute the norm by doing this inner product business. Okay, and you do that, and finally you find that this is the formula for the normalized adjoint block. This is the formula for the normalized singlet block, where we have used that in the case of the singlet, this is 1, and this guy is simple because this is not there. Okay, is this clear? I've gone fast, but Is this clear? Any questions? I just wanted to show you how simple these calculations are. You never have to do any calculations, you just draw diagrams. Okay. Okay. Now, in order to understand crossing, you need to express the identity block in terms of singlet and adjoint, sorry, antisymmetric, and adjoint block in terms of singlet and antisymmetric. Now, you can do that using Whittle's inner product by just taking this equation and taking inner products on both sides. So in order to find this quantity, we need to know this inner product and this inner product. Okay, so let's first, I'm taking these blocks and writing them in a way that makes it easier to take the inner products, putting all the insertions at the top. I do it in a particular way that's convenient for me. Okay, I'll come back to this. First, let's look at the computation of these, of the norm of GSA with GSA. Okay, using this representation of these blocks, gluing them, you get this thing, and then some processing. You cut here, you've got a 2-point function block, and then you can insert identity in space of 2-point function blocks, closing divided by this, to simplify this expression. You get an answer. In the end, the norm of this block you find is the quantum dimension of this block. Very satisfying. The norm of classical projectors were their classical dimension. The norm of these quantum projectors are their quantum dimension. You can show this is always true. Okay, not just in this example, it's always true. Okay, so in this formula where we needed to divide by some norm, the norms were just these quantum dimensions of these representations. Okay, now what remains is the most difficult calculation is to compute this cross inner product. There is one important complication here, which I will just mention and then tell you about only if there are questions. The complication is that in order to take this inner product, I need to deal with the fact that in this block, we had insertions like AF, FA, whereas in the earlier block, we had insertions like FFA. So before taking the inner product, I need to move this A, switch the positions of this A and this F. Okay, this is an ambiguous operation because it depends on which way you do it. You can do it from above, you can do it from below, you can wind 20 times into it. It's a sheet structure ambiguity. The way we did the calculation is we made one choice, then we did it for all choices, and then we gave the interpretation for all how they're all the same. Okay, so right now I'm presenting the calculation with one choice of this sheet structure ambiguity. Okay, I won't go through it. Given the time, there is some Wilson loop you have to compute, expectation value you have to compute. You go through a series of manipulations, most of which are presented, or simple generalizations of those that are presented in Witten's paper. And you go through these manipulations and you get a final answer for this inner product. Always, cutting diagrams, inserting completeness, doing various twisting, doing various things. Okay, similarly with the adjoint. So the final, and these things are presented in terms of some numbers here, which can be computed. Again, I'm not going to go through the details, and you get this answer for these numbers. Okay, putting it all together gives you an expression for the symmetric and antisymmetric blocks in terms of singlet and adjoint blocks. This is our final answer.
You say you're saying that the cross product is not ambiguous, although it looks ambiguous.
The cross product is ambiguous, but I'm going to remove that ambiguity with an interpretation. Now, the interpretation you either buy or not buy, but as algebra, it is ambiguous. We'll come to that. Okay. Before getting to that important question, I will finish in like 3-4 minutes. Before getting to that that important question, we can also now these theories are conjectured to be level rank dual to each other. So these crossing rules, if they're correct, and if duality is correct, should be consistent with this level rank duality. Okay, I haven't told you what this Q is, but most of you know what Q numbers are, right? Q to the power m minus Q to the power minus m over Q to the power 1, or maybe with a 2. Q to the m by 2, I mean, m by 2. Q to the power m by 2 minus Q to the power minus m by 2 divided by Q to the power half minus Q to I'll write that down. This is what an M number is, a Q number is, Q deformed M. Okay, fine. So this is what we get. Now, it is, if this is true, then we can go to the dual frame and use this rule in the dual frame. We get something. Then we want to know what is the relationship between these two crossing points. Okay. By doing by putting in the duality transformations, you can easily check that these blocks have the same crossing rules as these blocks. The dual blocks with symmetric and antisymmetric interchange, and also an extra minus sign, have exactly the same crossing rules as the original blocks with symmetric and antisymmetric where they were without that X and not without that interchange. But interchange between symmetric and antisymmetric is what we expect for duality, because that's how level rank duality works, maps symmetric to antisymmetric. Indeed, in our earlier calculations from 8 years ago with Penta, this is exactly what we found, that the map interchange symmetric and antisymmetric up to this minus sign. Yes. Yes, it's a strong weak duality. It's called level rank duality in terms of in the context of Chern Simons theory. Yes. Okay. So these crossing rules here are consistent with level rank duality. Okay. Now, finally, once I've got the blocks, I can see how the S matrices themselves transform under crossing. I've written the answer here, and I put this superscript 0 here, and that is to answer your question. Okay. We did this calculation with one choice of sheet ambiguity. But as I said, there were an infinite number of possible sheet choices we could have made. We labeled those sheet choices by n and repeated the calculation for each of those choices. And we get this answer. We get this answer here for the crossing rules. Okay? Same answer up to a phase, up to a different phase. Now, you see, if you are willing to absorb this phase into this tau, they're all the same answer. At first, this sounds good, because it's a general principle in quantum mechanics that overall phases have no meaning. You know, an S matrix and overlap between an initial and a final state, but you could have chosen the same initial state, but chosen the phase to be different. Somebody else could have chosen a different phase. That would have changed your S matrix. That sounds good. However, you have to be very careful. You have to be very careful because overall phases are meaningless in quantum mechanics, but relative phases have meaning. Okay, and remember here we're dealing with tau, but the full S matrix was 1 plus I tau, or whatever, cos pi, whatever, cos something I plus I tau. Okay, so our conjecture, and we have some words but no calculations to support this. This is the weakest point in our paper. Our conjecture is that the crossing relations, when we get these crossing relations with these taus, with these extra phase taus, that gives us taus in a frame where the identity part also gets that extra phase. That is that the overcrossing that you do going from one to the other also affects identity. We can.
You mean it also affects identity?
Meaning?
They're like different. You have to. They're different crossing processes. You're labeling the S matrix by different sort of trajectory S matrices.
Yeah, no, it would be a different phase, a gauge. It would be this. But suppose I have, I'm not writing the cos pi. It's irrelevant for this. Suppose I have I plus I tau times e to the power I sub phase.
So just
overall phase is, this is my conjecture. That this phase, if this phase was overall, not just in the tau, but also an identity, then it's physically meaningless. And the conjecture is that these different crossing rules give you the crossing for S matrices written with different phases of identity.
But how do you know what was the original phase of identity?
Yeah, all that matters is the relative, relative phase. Yes.
I mean, for this particular crossing,
yes,
you are saying for one particular crossing is just identity, not.
Between this crossing and that crossing, identity picks up this extra phase.
Yeah, that I understand.
But what is the absolute phase?
Yeah, so with the
yes, yes. What is the absolute phase? Okay, there we know the answer, at least in this case, because we know the answer in our calculation. So we know what gives us the correct unitarity relations. So this is our final. So our final conjecture is this, that each of these is this phase times a universal guy. Okay, that is true for tau is not a conjecture, it's true. Okay, the conjecture is that it's also true for this identity piece, and that this universal guy comes with no phase. Okay, how do we know that? I don't have a clear argument, but this is the thing that will match our calculation.
When the inside this universal thing, you could have absorbed
some arbitrary phase, yes.
By
yes, and that would have been a disaster because that would be physical.
Yeah.
Okay, I don't understand this properly well, don't have a clear argument, but the only way it can all work out and match our thing is if this universal guy was just genuinely identity with no phase. Yeah, so in that limit, it has to be this, but the phase could be like k dependent, right? Right. This part we need to understand better. Yes. Yes.
Choice of different sheets
is probably there. Yes, and the choice of different identity phases. One thing you can do, just to justify this a little more, is if you do Arnold-Bohm scattering in different gauges, then you get identity with different phases. This is a true statement. Yeah, so that phase related to what you're saying. What?
Is it the same?
I think so, because going from one sheet to another, and these gauges are very. I think so. Yes, yes. For instance, if you take a phase where the gauge field is 0 here and pi here, 2 pi, whatever. See, the phase where you had e to the power I nu by 2 and e to the power I nu by 2 will give you identity with no phase. You could go to another gauge where you get e to the power I nu and 1. And that will give you identity with the phase e to the power I nu by 2. Okay, so different choice of gauge. Where you put your cut in the gauge affects this answer. And that cut is somehow related to this thing. But this part I feel I don't understand as well as I should. Yes. Sorry, what was your question?
Shouldn't the scattering matrix be gauge invariant?
No, the scattering matrix is not gauge invariant. Gauge, you see, under gauge transformation, charged states with charged particles pick up a phase. Okay, and our initial states have changed with states with charged particles. So under gauge transformations, the scattering matrix is not gauge invariant, but it transforms only according to a phase, because we're scattering gauge dependent quantities. But more, yeah. This is a general thing in quantum mechanics, the phases of, yeah. Okay, so this part I would like to understand better. However, okay, take it or not, this is our conjecture. Okay, fine. So with this conjecture, we get this beautifully simple. So basically the question is, what are the scattering rules for the taus whose identity part is genuinely identity? Okay. If you buy our, the conjectures that went in here, we conclude that when you've chosen the scattering part to be genuinely identity, this is the scattering. This is the crossing. It's a very beautiful crossing rule, because you see it's exactly the same as the classical crossing rule without the Qs. Exactly the same. So it's a Q deformation of the classical scattering rule. Okay. Now, if you take this rule and you take the 't Hooft limit, you can check that this is what it reduces to. This is the factor of sine pi lambda by pi lambda that we found by explicit calculation in our papers. Yeah.
Go back to the previous slide. You're saying that whatever we did with global symmetry,
yes.
45.
Yes.
We place that ordinary global symmetry 2 by 1.
Yes.
Again, still as global symmetry. Then we get the same.
Perhaps those words about the quantum group and the global symmetry are the correct thing to say. But yeah, that sounds reasonable. That sounds reasonable. Good. Yeah. I know the quantum group so little that I hesitate to put it in those words. But
at least all this gauge field expression.
Yeah, it's all gone. It's all gone. It's all gone. Yeah, exactly.
Except for some denominator.
Exactly. So what would be really cool is if there was a natural definition of 6J symbols for the quantum group that gave this answer.
There are 6J, quantum 6J.
Yes.
Quantum group, that's well known.
That's well known. And if somebody like you could compute them for FF to AA and see what you get.
I mean, they are in a sense the same thing, like G1, G2, and
yeah.
Klebsch-Gordons and
Klebsch-Gordons and so on.
Yeah.
But the whole structure of tensor products in the quantum rule is different. Group is different, right? It's not quite the normal tensor product, as you know. You have to put extra phases. It's some complicated thing. I've not seen my little. Yeah. I'm sure it plays a role somehow. But if somebody is good enough at these kind of things to calculate and tell me what these 6J symbols are, I'm sure it's known in some way. Somebody could. Yeah. I was not able to find it, but that means nothing. Okay. Fine. But if it's not known, it doesn't matter. This is the answer. Okay. Fine. So I'm ending with some discussion. In 1 minute, I'll stop. First, we presented systematic procedure to determine the rules for crossing symmetry in an arbitrary matter Chern Simons theory of finite n and k. Our method has passed some checks, but also, as you see, has some irritating phase ambiguities. It would be nice to understand that. Okay. It would be interesting to perform additional checks of this proposal, for instance, by scattering in mass deformed ABGM. The context here is that people have done various calculations in this theory, and they get answers that conflict with unitarity, probably because they're using the wrong structure of the S matrix. Can we cure this, test our formalism, help understand their formalism? Okay. Would be interesting to reiterate these results from a direct analysis of Feynman diagrams. Perhaps these structures, these conformal blocks, come out as a result of sort of quote-unquote IR divergences in these theories. Perhaps there's a relation to celestial holography, because these conformal blocks are tightly related to these Wess-Zumino-Witten modes. And Wess-Zumino-Witten modes are modes created by large gauge transformations. And modes created by large gauge transformations are the stars in celestial holography. Okay. Would be good to better understand these global issues related to discussion of conformal blocks, these phases, basically. Okay. It would be interesting to generalize our discussion. I presented the discussion just for Chern Simons theories coupled to massive matter. It would be interesting to do this for arbitrary topological theories. I have the feeling that somebody who's good at mathematics, someone like Naveen could do this for breakfast. It's probably all these ideas. Just, yeah. Okay. It would be interesting to find more additional explicit answers. For instance, we found these explicit answers for 2 fundamentals, 2 antifundamentals. It would be nice to do it for adjoints. It would be nice to do it for bifundamentals in ABGM theory, for SON, SPN, and to see whether it's always the case that the classical answers are Q deformations of the quantum answers. Okay. It would be interesting to rerun the S matrix bootstrap with these modified crossing relations. People have been, of late, this has been a very popular game, right? Finding constraints on the S matrix from crossing and unitarity and analyticity. Now, crossing changes, so it changes the constraints. Is that an interesting new program, a modification of that program one can run with these crossing equations? And I think it would, last point is it would be interesting to formulate the Boltzmann transport equation with these modified S matrices. This sounds a bit far out, I know, to most of you, but I think it's interesting for the following reason. The Boltzmann transport equations for bosons are different from the Boltzmann transport equations for fermions. Basically because if a state is occupied, bosons like to go to that state, whereas fermions cannot go to that state. Okay. Now, in these theories, the S matrices have different structural properties that in some way interpolate between those of bosons and fermions. So I think you're going to get a different Boltzmann transport equation for these theories, anionic Boltzmann transport equation. Okay. Now, this Boltzmann transport, one of the nice things about a Boltzmann transport equation is that it leads to equilibrium. Now, the bosonic Boltzmann transport equation leads to Bose-Einstein statistics. Fermionic Boltzmann transport equation leads to Fermi-Dirac statistics in equilibrium. There's a conjecture for what equilibrium these equations should lead to. This is the conjecture that Naveen, Amio, and I had in a paper we wrote a year ago. With these modified, these Q-deformed Bose statistics, Q-deformed Fermi statistics. It would be really cool if we could understand these Boltzmann transport equations and find that the equilibrium of that was our statistics. Okay, I'm stopping here. Sorry for having gone 1 hour over time.
Shiraz, I have a question. Can I ask?
Yes.
With the let's say with your conjecture of both the prefactor analog of sin pi by lambda by pi lambda and the exponent near the identity, those 2 factors.
Yes.
Can I just construct a simple S matrix and check that the unitarity holds? For example, if you remember, for n is equal to 2 superangles, n is equal to 2 case, it was just at the tree level and it did not get modified. And the way unitarity worked was that the tree level thing gave you the delta function, and then that's how things worked out. So would I just be able to take your factors and multiply with the tree level and check the unitarity holds, or is there some simple example where I can just construct one example?
Yeah, you mean you take a unitary S matrix, do crossing on that, and check whether unitarity works on the other side as well.
Yeah, exactly. Like just like we wrote down a S channel or the singlet channel S matrix, which was unitary with this modified factor.
Yes.
So here you did not compute the momentum dependent factors, right? If I understood correctly.
No, we've done no compute.
Can I just find out one simple example, maybe the tree level Chern Simons theory, because it produces a delta function if I convolute it. So would that be a example of a answer with your?
So you'd need one answer exactly. You're saying there's a conjecture for one exact answer on both sides. This n equals 2. The conjecture is that it's tree level exact. Huh?
Yeah.
Yeah. Even at loop level, that's tree level exact.
Yeah.
Now ABGM was not tree level exact. So.
No, Shiraz, I did not mean that. What I meant was that, can I just simply construct, let's say I take tree level amplitude and multiply with your prefactors?
Yes.
And
will that be a consistent full amplitude you're saying?
Yes.
I doubt it, right? Because there's like this theorem, right? This Axe theorem that in any non-trivial unitarity theory, scattering has to happen. In even more than 2 to 2, scattering has to happen. But maybe I'm not understanding you, Sachin. Maybe we can talk.
Yeah. Okay.
But I'm perhaps not understanding you. But somehow doesn't sound likely to be. But maybe yes. I'm not sure.
One example I was giving, n is equal to 2 case we computed. This was one precise example where the tree level answer multiplied with this non-trivial factor was unitary. So
this factor was this cos pi lambda?
Yeah.
And then what about the non-trivial part of the amplitude?
Yeah, that was just the tree level answer, right? No,
and the tree level with meaning with the sine pi.
Yeah.
And that was saturated unitarity by itself without like 2 to 4 scattering, for instance. Or is this large n or finite n?
Yeah, large n. Oh,
large n. I see.
Finite.
Now I understand. Now I understand what you're saying. I see. So that would be about roughly the same level as same kind of check that we did in the non-supersymmetric theory.
Yeah.
I think that. Sorry. Now I understand. Yeah, of course that should work, and I think it will work, right? Because it's in large n, all you see is this one factor.
Right. Okay, sir. So, sorry. Yeah.
No. Thank you.
Another quick question, maybe.
I have a quick question. I mean, in that FF loop that you inserted in order to prove the identity, conjecture or whatever, couldn't there be corrections to that loop, and would those change things?
Which loop?
The FF loop.
FF loop.
The F loop that can you go back to yours? Yeah.
Which one?
No, previous, much ahead. Yeah, even further. Yeah. No. Yeah. So the previous one.
Yes.
Even the previous. The previous one. Yeah, this one. So
yes.
This FF loop, could there be corrections to such a loop?
There are no corrections. This is exact. This is all calculations of pure Chern Simons theory. Everything here is exact.
So it's one loop exact, you are saying.
If you call this one loop, the answers for these Wilson loops are complicated functions when you expand them in 1 over k. So they're not one loop exact in the sense of Feynman loop diagrams. Right? For instance, this expression here is like q to the power n minus q to the power minus n over n by 2 minus q to the power minus n by 2 divided by q to the power half minus q to the power minus half. Q is equal to e to the power 2 pi by I k by I times kappa. E to the power 2 pi I divided by kappa. Okay, expanding in a 1 over kappa series gives you an infinite expansion. So each of these is a complicated expression, but they're all known exactly. I hope this is answering the question, Joe.
Yeah, so you're saying that I mean, though it looks like a single loop, it's actually a
Yes,
single...
yes. In terms of Feynman diagram loops, each of these is infinite.
Okay, if there are no other questions, let's thank Shiraz for a very detailed and interesting talk.
I should apologize for taking so long. Sorry.